BM25 is not your only option. Ship a language model ranker into OpenSearch and see when it wins. By the end, you will understand what query likelihood ranking with Dirichlet smoothing does, why it behaves differently from BM25, and how to experiment with it in a small OpenSearch setup. I'm Professor Pi, teaching search and IR with simple Python. Search teams pick query likelihood when they want a probabilistic voice for documents. It answers this question. Given a query, how likely is each document to have generated those words? That viewpoint fixes some BM25 oddities when queries are very short or documents are very short. OpenSearch already exposes a built-in similarity called LMDirichlet that implements this idea efficiently inside Lucene. Using OpenSearch saves you from re-implementing inverted indexes and scoring from scratch, and it gives low latency for small to medium collections. At a high level, a model scores documents by imagining each document as a small language model. If a query word is rare in the document, the model borrows probability mass from the whole collection using Dirichlet smoothing. That prevents zero scores and balances document evidence and collection commonness. Intuitively, Dirichlet smoothing has one knob named mu that controls how much to trust the document versus the whole collection. Small mu trusts the document more. Large mu relies more on the collection frequency. We will build a tiny pipeline to compare OpenSearch's LMDirichlet ranking with a simple custom reranker that applies the same Dirichlet formula on the search hits. This keeps the experiment clear. You will see how the built-in scorer and a transparent reranker agree or differ, and how changing mu shifts winners. Now, we will confirm the client can reach a local OpenSearch node. This snippet verifies that the opensearch-py OpenSearch client can talk to a local OpenSearch node. The code creates the client named client, pointing at localhost on the default port. The variable OK stores the result of client.ping, which confirms the node is reachable and responsive. The variable IDX holds the index name we will reuse across steps for consistency. Finally, the print shows whether connectivity is good and what index name we will operate on. Seeing ping OK equals true matters because every later create, index, and search call requires a live OpenSearch connection. Next, we will create an index configured to use the LMDirichlet similarity. This code prepares a fresh index in OpenSearch configured for the query likelihood model with Dirichlet smoothing. It first deletes IDX if present, so creation is clean and deterministic. The variable body sets the default similarity to LMDirichlet with mu equal to 1200, which instructs Lucene to score terms using Dirichlet smooth likelihood. The client.indices.create call applies this configuration when building the index. The print confirms the chosen mu value, so you can reason about smoothing strength later. This matters because we will compare OpenSearch's built-in LM scoring to a custom reranker that uses the same Dirichlet principle. Now we will index a tiny corpus and run a baseline LM search. This example seeds a tiny corpus and runs a query using OpenSearch's LMDirichlet ranking. 3 short documents are indexed into IDX, covering banana, pie, and distractor terms. The refresh ensures the newly added documents are visible to subsequent searches. The variable s stores the client.search response for the query banana pie, with size set to 3 candidates. The variable hits reads the top-ranked documents as scored by the LMDirichlet similarity configured earlier. The final print shows which document is currently top-ranked and how many results we examined, setting a clear baseline for later re-ranking. Next, we will take those hits and recompute scores locally using the same Dirichlet math so the behavior is explicit. This snippet applies a custom query likelihood with Dirichlet smoothing over the open search hits. The list D pairs each document ID with its tokenized text, and C concatenates all tokens to build a tiny collection model. The dictionary P maps each token to its collection probability, which the Dirichlet formula needs for smoothing. The variable mu sets smoothing strength. Here, 200 rewards term matches more aggressively by relying less on collection priors. The variable R holds documents sorted by summed log probabilities over the query words banana and pie. The printed top ID and log probability show our custom reranker's current winner and its strength. Now, we will change the mu to see how smoothing strength changes the rerank order and score stability. This code demonstrates how changing Dirichlet's mu affects custom rerank behavior over the same open search hits. The variable mu is raised to 2,500, which leans more on collection probabilities P and less on document term frequencies. The expression recomputes each document's summed log likelihood for banana and pie using the new smoothing. A larger mu typically stabilizes scores, reduces overfitting to short documents, and can narrow gaps between candidates. The final print shows the new top ID and its log probability, making any shift in magnitude or winner explicit. This confirms you can tune smoothing to balance recall and precision for your domain. If you map this toy run to a real search pipeline, replace the 3-document corpus with your FAQ or product descriptions, and run the OpenSearch LMDirichlet index in parallel with the existing BM25 index. Use the custom re-rank only on the top candidates to keep latency low. The same mu behavior will guide how conservative or aggressive your re-ranker is on short snippets versus longer documents. Recap. What it is query likelihood with Dirichlet smoothing treats each document as a tiny language model and scores how likely the query came from that model. When to use it. Try it when queries are short, documents vary widely in length, or you want a probabilistic baseline that adapts to collection frequency. One caveat. Tuning mu is critical because it directly controls the trade-off between document evidence and collection priors. Next step. Tune the mu value on real data and measure ranking shifts. Run the same pipeline over a larger corpus. Log timing for top K candidates and plot precision or relevance change as you sweep mu to find the sweet spot. If short practical IR helps, subscribe and watch the IR videos.